Often when debugging, we find ourselves with the problem of having an input that crashes a program, but not knowing what aspect of the input is causing the program's failure. For example, a web page with hundreds of lines of HTML crashes a browser, or a random sequence of keystrokes crashes a smartphone app. Isolating the cause of the failure would be enormously helpful in finding out what change needs to be made to the program's code. One automated technique for reducing large failing inputs is delta debugging. Delta debugging is based on the scientific method: hypothesize, experiment, and refine. By selectively and systematically removing portions of the input, delta debugging automatically removes irrelevant information from a failing test case in order to attain a minimal bug-inducing input. A typical bug report contains a lot of information that the developer can use to reproduce the program failure. Once we have reproduced a program failure, we must find out what information is relevant. For instance, does the failure really depend on 10,000 lines of code? Does the failure really require this exact schedule of events? Does the failure really need this sequence of function calls? Simplifying the information in a bug report down to only what is relevant is important for several reasons. First is ease of communication. A simplified test case is easier to communicate to members of the development and testing team. Second is that simpler test cases lead to easier debugging. A smaller test case results in smaller states and shorter executions. Third is that it allows us to identify and collapse duplicate issues. A simplified test case can subsume test cases in several different bug reports. Let's look at a real-world scenario which should help motivate the necessity for bug minimization. In July of 1999, Bugzilla, the Mozilla bug database, had over 370 unresolved bug reports for Mozilla's web browser. These reports weren't even simplified, and the bug queue was growing by the day. Mozilla's engineers became overwhelmed with the workload. Under this pressure, the project manager sent out a call for volunteers for the Mozilla Bugathon, volunteers to help process the bug reports. Their goal was to turn each bug report into a minimal test case, in which each part of the input is significant in reproducing the failure. The volunteers were even rewarded with perks for their work. Volunteers who simplified 5 reports would be invited to the launch party, and those who simplified 20 reports would receive a t-shirt signed by the engineering team. Clearly, Mozilla would have benefited from an automated bug minimization process here. Let's look at a concrete bug report in the Mozilla bug database. Consider this HTML page. Loading this page using a certain version of Mozilla's web browser and printing it causes a segmentation fault. Somewhere in this HTML input is something that makes the browser fail. But how do we find it? If we were the developers of the Mozilla web browser that crashes on this input, we would want the simplest HTML input that still causes the crash. So how do we go from this large input to this simple input, a mere select tag that still causes the crash? What do we as humans do in order to minimize test cases? One possibility is that we might use a binary search, cutting the test case in two and testing each half of the input separately. We could even iterate this procedure to shrink the input as much as possible. Even better, binary search is a process that can be easily automated for large test cases. Let's see how this application of binary search might work. This bar here represents the original failure-inducing input to a program. If one half of the input causes the program to fail, then we can eliminate the second half of the input and attain a smaller failure-inducing input. We can repeat the procedure on the new, smaller failing input. In this case, the first half of the halved input causes the program to fail, so we can throw away the second half. We are left with an input that induces a failure, but which is a quarter of the size of the original input. Repeating the procedure, we might find that the first half of the new input does not crash the program, but that the second half does cause the program to fail. In this case, we'd remove the first half and keep the second half to obtain yet a smaller failure-inducing input. Iterating again, we might find that the first half of the new input does not crash the program, and so does the second half. In this case, binary search can proceed no further. The simplified input is this dark green portion of the bar, 1/8 the size of the original input, which is good progress. We can apply the binary search algorithm to minimize the number of lines in the HTML input that we saw earlier, the one that crashed Mozilla's web browser. We'll assume line granularity of the input for this purpose. That is, we will only partition the input at line breaks. The algorithm outputs the following line, simplifying from 896 lines in the original input to this single line in only 57 tests. Suppose that we wish to further simplify this input using character-level granularity to obtain the desired output comprising only the select tag. Let's see how the binary search algorithm works this time. The initial input consisting of the entire line causes the browser to crash. The first half of the line doesn't cause the browser to crash. And the second half of the line also doesn't cause the browser to crash. At this point, binary search says we are stuck, since neither half of the input induces a failure on its own. Is there some other way we can minimize the input? Let's generalize the binary search procedure a bit. Instead of requiring ourselves to divide inputs strictly in half at each iteration, we could allow ourselves more granularity in dividing the input. Perhaps we could divide up our input into many possibly disconnected subsets at an iteration, and only keep those which are required to cause failure. In particular, we can break up the input into blocks of any size, called changes from the original input. The traditional use of the Greek letter delta for change is the origin of the name delta debugging. We can then use subsets formed from these blocks. Perhaps we just use a single block. Perhaps we use several blocks concatenated together. Or perhaps we use non-contiguous blocks. For example, block delta 1 and block delta 8 to form subsets for testing. Take a moment to consider what might happen if we allow the granularity of the input changes we use to be finer or coarser. Finer granularity means our input is divided into more smaller blocks. Coarser granularity means that our input is divided into fewer larger blocks. What would happen to the chance of finding a failing subset of the input? And how much progress would we make if we found a failing subset of the input? Fill in each box with the appropriate letter. A for slower progress, B for higher chance of finding a failing subset, C for faster progress, and D for lower chance of finding a failing subset. By testing subsets made up of larger blocks, that is, coarser granularity, we lower our chance of finding some subset of the blocks that fails a test, but we have fewer subsets that we need to test. Additionally, upon finding a subset of blocks that fails, we can eliminate a large portion of the input. This means our progress towards a minimal test case is faster. On the other hand, by testing subsets made up of smaller changes, that is, using finer granularity, we have more subsets that we have to test. And upon finding a subset of changes which causes failure, we typically can only remove small portions of the input. These both slow our progress towards finding a minimal failing test case. However, the trade-off is that by testing more subsets, we increase our chance of finding a smaller subset that actually does cause a failure. Indeed, we could go so far as to make the granularity of the input changes 1 character in size, which would guarantee that we find the minimum failing test case. But this strategy in the worst case would take exponential time in the length of the input. The delta debugging algorithm combines the best of both approaches. At first, it divides the input into larger blocks, and it tests all subsets of these changes for failure. As the algorithm becomes unable to find subsets that fail the test, delta debugging increases the granularity of its changes, testing subsets formed from smaller blocks for failure. Let's see how delta debugging would proceed with our earlier example. Recall that neither half of the original input string causes a crash in Mozilla's browser, since neither half contains the entire select tag. Using delta debugging, we increase the granularity of the blocks we will use to create subsets by decreasing the size of the blocks by a factor of 2. We first test the subset formed from the second, third, and fourth blocks. This subset doesn't cause a crash since it does not include the entire select tag. Next, we test the subset formed from the first, third, and fourth blocks. This does cause a crash since it includes the select tag. So we can eliminate the second block from consideration altogether. Next, let's see what happens if we keep only the first and fourth blocks. Again, this causes a crash since it includes the select tag. So we can eliminate the third block from consideration. Removing the fourth block causes the input to pass the test, as the closing bracket of the select tag is missing in this input. Therefore, we would end up keeping the first and fourth blocks and increasing the granularity before continuing to test subsets, until we eventually end up with the minimal failing input comprising only the select tag after 48 iterations. Now that we have seen an example of how delta debugging would work in practice, let's formally define the algorithm so that we can analyze its properties and prove that it will work as expected. Let R be the set of all possible inputs that we wish the delta debugging algorithm to consider. We will use RP to denote an element of R on which the program passes, and RF to denote an element of R on which the program fails. An example of RP is any of the following passing inputs, such as this one. An example of RF is any of the following failing inputs, such as this one. The key building block in the delta debugging algorithm is the concept of a change, which is how one input is transformed into another. Formally, a change delta is a mapping from the set of all test inputs to itself. In other words, it is a function which takes a test input R1 and returns another test input R2. The operation of inserting this string between the 10th and 11th character positions of the input would be an example of a change function that is relevant to the Mozilla example from before. Other examples of change functions are the operation of concatenating a semicolon at the end of a string, removing the first character of a non-empty string, and reversing the order of a string. Even the function that simply returns its input string is a change. It serves as the identity change function. We next introduce the concept of decomposing a change function into a number of elementary change functions, such that applying each elementary change in order to the input R has the same effect as applying the original change to the input R all at once. For example, suppose deleting a line from an input file results in a failure. We can decompose this deletion into a sequence of individual character deletions. Looking again at our Mozilla example from before, we can decompose the change denoted by delta prime, which represents inserting this string at input position 10 into elementary changes as follows. Delta prime equals delta 1 composed with delta 2 composed with so forth up to delta 10, where delta 1 is the change that inserts the character M at position 10, delta 2 is the change that inserts the character E at position 11, and so on. Note that what we consider an elementary change can depend on the context of the problem. We could consider insertions and deletions of lines in a file to be elementary, or if we are using delta debugging on a set of binary parameters for a program, an elementary change might be switching one bit on or off. Let's review the setup we have going into the delta debugging algorithm. We have an input on which a program passes, RP. We have an input on which a program fails, RF. And we have a set of elementary changes, which we will call CF, such that applying the changes in order to RP yields RF. Note that RP is typically a simple input on which the program trivially passes, such as the empty input, and RF is typically a complex input on which the program fails, and that we would like to minimize. In the case of Mozilla's web browser, RP could be a blank HTML file, and RF is the full HTML file that causes the browser to crash. Subsets of CF will be important in the delta debugging algorithm, so we will distinguish them henceforth by calling them test cases. Given a test case, that is, a subset of the changes, we want the ability to apply that subset of changes to the passing input RP and determine if the resulting input causes the program to fail in the same manner as the failing input RF. To formalize this notion, we define the function test, which takes a subset of CF and outputs one of 3 characters based on the outcome of our test. We distinguish these 3 test outcomes following the POSIX standard for testing frameworks. If the test succeeds, the test function outputs pass, written here as P. If the test produces the failure it was intended to capture, the test function outputs fail, written here as F. And if the test produces indeterminate results, then the test function outputs unresolved, written here as a question mark. The goal of delta debugging is to find the smallest test case C such that test applied to C returns F. In other words, to find the smallest set of changes that we need to apply to passing input RP in order to result in the same failure as the failing input RF. We call a failing test case a global minimum of CF if every other smaller sized test case from CF does not cause the test to output F. In other words, any smaller sized set of changes either passes the test or causes the test to be unresolved. The global minimum is the smallest set of changes which makes the program fail. But finding the global minimum may require performing an exponential number of tests. If the set CF has size n, we need to perform, in the worst case, 2 to the power n tests to find the global minimum. Instead of searching for the absolute smallest set of changes that causes the failure, we can approximate a smaller set by reformulating our goal. We will find a set of changes that causes the failure, but removing any single change from the set causes the failure to go away. Such a set of changes is called one minimal. More formally, define a failing test case C to be a local minimum of CF if, for every proper subset C' of C, applying the test function to C' doesn't produce a failure. This is in contrast to a global minimum in the following way. For a local minimum, we only restrict our attention to subsets of the local minimum test case. For a global minimum, there must be no smaller test case that causes a failure. Define a failing test case C to be n minimal if, for every proper subset C' of C, if the difference in size between C' and C is no more than n, then the test function applied to C' does not cause a failure. In other words, C is n minimal if removing between 1 and n changes from C causes the test function to no longer fail. Just as local minimality is a weakening of the notion of global minimality, n minimality is a weakening of the notion of local minimality. And one minimality is the weakest form of n minimality. A failing test case C is one minimal if removing any change from that test case causes the test function to no longer fail. Even though one minimality is not nearly as strong as global or even local minimality, we focus on it because it is still a strong criterion. It says that the test case cannot be minimized incrementally, and we can program an efficient algorithm for applying and testing incremental changes. Let's stop here to check your understanding of the different types of minimality with a quiz. Suppose a program takes a string of A's and B's as input, and it crashes if given an input with an odd number of B's and an even number of A's. Because BABAB has an odd number of B's and an even number of A's, it is a failing input to the program. If we take RP to be the empty input and RF to be BABAB and consider inserting each character to be a separate change, then CF will be a set of 5 elementary changes. Previously, we defined a test case to be a subset of these changes, which was a set of delta functions. For brevity, we won't use the delta notation in this quiz. Instead, we'll slightly abuse terminology and just consider test cases to be the subsequences of BABAB that result from applying those changes in a subset of CF. Here, I'd like you to enter 4 failure-inducing test cases that are subsequences of the input BABAB that satisfy the following constraints. First, find the global minimum test case, that is, the smallest possible failing subsequence. Second, find a local minimum that is not the global minimum. Third, find a one minimal failing test case of size 3. And lastly, find a 2 minimal failing test case of size 3. If no subsequence of BABAB exists that satisfies the constraints, enter the word none instead. Let's start with the global minimum. Notice that the program crashes only on non-empty inputs, since we need to include at least one B to have an odd number of Bs. So we start by considering subsequences of size 1. The only input of size 1 with at least one B is the string consisting of just B. This subsequence fails the test. It has one B, an odd number, and 0 A's, an even number. Since B is the smallest possible failing subsequence of BABAB, it is the global minimum failing test case. Next, let's try to find a local minimum that is not a global minimum. Remember that no proper subsequence of a local minimum can fail. But earlier we said that all failing subsequences will need at least one B. So every failing subsequence of BABAB itself has a failing subsequence B. So the only local minimum is B itself. So there are no local minima that are not global minima. Now let's try to find a one minimal failing subsequence of BABAB of size 3. We need at least one B, and we need an even number of A's. This means we can either have 2 A's and 1 B, or 3 B's. There are 4 subsequences of BABAB that satisfy this criterion: AAB, ABA, BAA, and BBB. Now, let's see which of these are one minimal. Remember that a failing test case is one minimal if, no matter which change we remove, we get a passing test case. Now, removing one character from any of these strings results in changing the parity of either the A's or the B's, meaning that the new subsequence will not cause a crash. Therefore, all of these subsequences are one minimal. Are any of them two minimal, however? This means that in addition to removing one character, removing any 2 characters arbitrarily still causes the subsequence to pass. In this case, however, by removing 2 characters and leaving just a single B, we obtain a failing input. Therefore, none of these test cases are too minimal. Now, let's think about how to build an algorithm to find a one minimal subset of a given set of changes C. We would then apply this algorithm to find the one minimal subset of the set of all changes by setting C to CF. One straightforward approach that might occur to us is to do the following. Iterate through each change delta I in C, testing whether the set C minus delta I fails or not. If we find a change delta such that C without delta still induces the failure, then we can call the algorithm recursively on C prime equals C minus delta. On the other hand, if every change's removal causes the test to stop failing, then C is one minimal, and so we return C. How well does this naive approach work? Well, in the worst case, we would remove the last change in the list per iteration after testing all previous changes. If we start with n elements, then we perform up to n minus I tests on the ith iteration, starting from iteration 0. The total number of tests in the worst case would then be n plus n minus 1 plus n minus 2 and so forth. For large values of n, this is approximately 1/2 of n square, or big O n square in asymptotic notation. We can often attain better performance than the first simplest algorithm that we thought of. Let's try to see if we can improve our algorithm's performance by making some modifications. What's one place where we are losing time in our algorithm? Recall our discussion earlier about the strengths and weaknesses of coarser versus finer granularity. Checking one change at a time is very fine granularity, which allows for a greater chance of success in finding a failure-inducing subset of changes. But it is also more time-consuming. If we start with very coarse changes at first, we might be able to save a lot of time. Only if we can't make any progress should we refine our granularity and increase the number of subsets we test. Here is a sketch of the delta debugging minimization algorithm invented by Andreas Zeller, who originally proposed delta debugging. The algorithm finds a one minimal test case from the given set of changes CF. It starts with n equals 2 and divides the set CF into n pairwise disjoint pieces called delta 1 through delta n. We use capital deltas here to represent subsets of CF instead of individual changes in CF. We also use nabla, the upside down capital delta, to represent the complement in CF of each capital delta. In other words, all the changes in CF which aren't in delta I are in nabla I. The algorithm then applies the test function to each delta I and to each nabla I. If one of these test cases fails, then the algorithm reduces the current input down to the input obtained by just applying the changes in the failing test case. If none of the test cases fails, though, then the algorithm refines its granularity by doubling n and recomputing new subsets delta I and nabla I. Here is the algorithm again, this time in more structured pseudocode. It has two parameters, n and delta. It starts with n equals 2 and delta equal to CF, which is the full set of elementary changes. Given n and delta, the algorithm divides delta up into n pieces, delta 1 through delta n, and computes their complements, nabla 1 through nabla n, appropriately. It then tests each delta I and each nabla I using the test function. There are three possible outcomes. If some delta I causes the test function to fail, then we go back to step 1, this time with delta equals delta I and resetting n to 2. Otherwise, if some nabla I causes the test function to fail, then we go back to step 1, this time with delta equals nabla I and decrementing n by 1. If none of these test cases causes a failure, then we have two possibilities. If the granularity is not yet at its maximum, that is, n is less than the size of delta, then we return to step 1, leaving delta the same and doubling the granularity. If the granularity is already at maximum, that is, n is greater than or equal to the size of delta, then this means that each capital delta I consists of a single change, and removing any single change causes the test case to no longer fail. Therefore, the test case is one minimal and we stop. Let's analyze this algorithm's complexity and see how it compares to our previous attempt. Unfortunately, the worst case complexity of delta debugging minimization is still quadratic in the number of elementary changes. It could be the case that we need to subdivide until we reach maximum granularity, and then we remove one change at a time, effectively doing the same amount of work as the naive algorithm we saw before. As an exercise for yourself, try to come up with an example of a test function and family of inputs that would give this worst case scenario. The good news is that in the case where we find a failure in either delta 1 or delta 2 in each iteration, convergence to the one minimal test case takes only a logarithmic number of tests, much like binary search. Let's work through an example of the minimization algorithm in the form of a quiz. Suppose a program crashes whenever its input contains the substring 42. And suppose we start with the original failing string 2424. Assuming that each elementary change consists of inserting a single character, let's see how the algorithm would minimize this string. First, begin by filling in the number of partitions we would make of the string delta, and write in the strings that would form our test cases. Please separate the strings by commas, and don't surround the strings by quotation marks. Also, feel free to ignore duplicate strings. For example, if both delta 1 and delta 2 are the same in some iteration, you just need to write it once. Finally, if delta cannot be partitioned evenly into n groups, split it into groups as evenly as possible. In the first iteration, we start with n equals 2, and dividing delta equals 2424 into two even groups gives the same string for all of delta 1, delta 2, nabla 1 and nabla 2, which is 24. Since 24 does not cause the program to fail, we leave delta the same for iteration 2 but double the number of partitions to 4. Dividing up 2424 into 4 partitions yields delta 1 equals delta 3 equals 2 and delta 2 equals delta 4 equals 4. Then we have nabla 1 equals 4 to 4, nabla 2 equals 2 to 4, nabla 3 equals 244, and nabla 4 equals 242. Nabla 1 and nabla 4 are the only ones that fail, so we may choose either of them as delta and proceed. Either way, we would decrement n by 1 to get 3. If we picked nabla 4 equals 242, then our partition would yield delta 1 equals delta 3 equals 2, delta 2 equals 4, nabla 1 equals 42, nabla 2 equals 22, and nabla 3 equals 24. If we had picked nabla 1 equals 4 to 4 earlier in iteration 2, then our partition would yield the same set, except that 22 would be replaced by 44. Either way, the only failing test case would be 42, which we take delta to be next. We also decrement n to n equals 2. Finally, partitioning 42 into two parts gives us delta 1 equals nabla 2 equals 4 and delta 2 equals nabla 1 equals 2. None of these test cases fails, and we observe that n equals the size of delta. Therefore, our algorithm terminates and returns delta equals 42 as the minimized failing test case. In the rest of this lesson, I will illustrate the versatility of delta debugging using a series of case studies conducted by the author of the technique. You can learn more about these case studies as well as the delta debugging technique by following the link to a technical paper in the instructor notes. The following C program, denoted bug.c, causes GCC version 2.95.2 with optimizations enabled to crash. This program consists of three functions: mult, copy, and main. Suppose we wish to minimize this program to file a bug report on GCC. Delta debugging can be used to achieve this goal. For the GCC program, a passing input is the empty input. And for the sake of simplicity, let's model each change as an insertion of a single character. Then, in the terminology of the delta debugging algorithm, test RP denotes running GCC on an empty input, test RF denotes running GCC on bug.c, which is this entire input, and each change delta I denotes inserting the ith character of bug.c. We next write the test procedure to be provided to the delta debugging algorithm. This procedure consists of 3 steps. First, it creates the appropriate subset of bug.c. Next, it feeds this subset to GCC. Finally, it returns failed if GCC crashes and passed otherwise. We then run the delta debugging algorithm using this test procedure. In only the first 2 tests, the algorithm reduces the input size from 755 characters to 377 and 188 characters respectively. The test case now only contains the mult function. The copy and main functions have been eliminated. Reducing mult, however, takes time. Only after 731 more tests do we get a test case that cannot be minimized any further. This test case contains only 77 characters. This test case is one minimal because no single character can be removed while still causing GCC to crash. Notice how every superfluous white space has been removed. Even the function name has shrunk from mult to a single letter T, and the original loop has been converted into an infinite loop. But GCC still isn't supposed to crash. As GCC users, we can now file this one-line program as a minimal bug report. But where in the GCC code could the bug lie? We already know that it is related to GCC optimization. The crash disappears if we remove the -O option on the command line to turn off optimization. Now, the GCC documentation lists 31 different options to control optimization. It turns out that applying all of these options causes the crash to disappear. This means that some options in this list prevent the crash. We can again use the delta debugging algorithm to find the crash preventing options. This time, the passing test RP denotes running GCC with all options. The failing test RF denotes running GCC with none of the options, and each change delta I denotes removing the ith option. After 7 tests, the algorithm reports that option -f_fastmath prevents the crash. Unfortunately, this option is a bad candidate for working around the failure because it may alter the semantics of the program. So, we remove -f_fastmath from the list of options and rerun the delta debugging algorithm. Again, after 7 tests, it turns out the option -f_force_addr also prevents the crash. So far, we have determined that 2 of the 31 options prevent the crash. Running GCC with the remaining 29 options shows that the crash persists. So it seems we have identified all the crash preventing options. So this is what we can send to the GCC maintainers. The minimal test case that we found, the fact that the crash occurs only with optimization, and the fact that optimization options -f_fastmath and -f_force_addr prevent the crash. While we as GCC users cannot identify a place in the GCC code that causes the problem, we have identified as many failure circumstances as we can. Another application of delta debugging is in the minimization of fuzz input, in which a program is fed with randomly generated inputs and observed to see if it crashes. Typically, the failure-inducing inputs found by fuzzing are large. Delta debugging can be used to reduce such inputs down to smaller inputs, causing the same mode of failure. Recall from the lesson on random testing that Bart Miller and his team examined the robustness of Unix utilities by feeding them fuzz input, a large number of random characters. The studies showed that 40% of these programs crash when fed with fuzz input. The author of delta debugging successfully applied the technique to minimize the fuzz inputs that crash a subset of the Unix utility programs. For example, the technique only required 24 tests to minimize a fuzz input comprising 1,000,000 characters that crashes CRT plot to a single character that still crashes CRT plot in the same manner. Yet another application of delta debugging is to isolate changes to source code that cause program failure. You likely have had this experience. One day your program works fine, the next day it does not, and you need to figure out why. Perhaps the amount of code that's changed is quite large. For example, release 4.17 of GDB, the GNU debugger on Unix, changed 178,000 lines. After this release, GDB no longer integrated correctly with the Data Display Debugger, or DDD, a common graphical user interface for GDB. How should the GDB maintainers determine which change line or lines among those 178,000 lines is the culprit, the solution is to use the delta debugging minimization algorithm, with the passing input RP being yesterday's code and the failing input RF being today's code. This allows you to pinpoint what specific change is making the code to no longer work. Further reading on this topic can be found at the link in the instructor notes. As we close this lesson, let's recap the key concepts with the following quiz. Check all the statements that are true about delta debugging. The technique is fully automatic. It finds the smallest failing subset of a failing input in polynomial time. It finds a one minimal test case instead of a local minimum test case due to performance reasons. It may find a different sized subset of a failing input depending on the order in which it tests different input partitions, and it is also effective at reducing non-deterministically failing inputs. Let's tackle each of the statements in order. The technique is fully automatic. This is false because one has to define the space of input changes, or deltas, which is application specific, as well as what constitutes a passing versus failing program run under each possible input. Delta debugging finds the smallest failing subset of a failing input in polynomial time. This statement is also false. The algorithm does not find the smallest failing subset. Such a subset is the global minimum, which takes exponential time in the number of changes to find. Delta debugging finds a one minimal test case instead of a local minimum test case due to performance reasons. This is true. Finding a local minimum, in the worst case, can also take exponential time in the number of changes. Finding a one minimal test case, however, takes at worst quadratic time. Delta debugging may find a different sized subset of a failing input depending on the order in which it tests different input partitions. This statement is also true, and here's a simple example to illustrate why. Consider a program that fails if its input contains either A or BB. The input AABB therefore crashes. If the minimization algorithm examines AA before BB on the first iteration, then it will end up with a one minimal test case A. On the other hand, if it examines BB before it examines AA on the first iteration, it will end up with the one minimal test case BB. Delta debugging is also effective at reducing non-deterministically failing inputs. This statement is false. The algorithm only functions correctly assuming that program failure is deterministic. Let's conclude by reviewing what we have learned about delta debugging in this lesson. First of all, delta debugging, like random testing, is a technique as opposed to a tool that can be used out of the box. A limitation of the technique is that it is not readily portable across programs. It needs to be re-implemented for each significant system in order to exploit knowledge changes that are specific to the system. For example, a delta debugging implementation for testing whether Mozilla's browser crashes differs from one for testing optimization flags for the GCC compiler. These two scenarios have different notions of what constitutes an elementary change. Perhaps a line or a character is an elementary change for the browser, whereas a binary flag is an elementary change for the compiler. The good news is that the delta debugging algorithm is relatively simple and provides excellent payoff for the effort it takes to implement it. Therefore, it is worth re-implementing it across several systems.